All right, let's settle down. Let's go and get started. All right, so real quick, sign-in sheet. Let me get this passed around. So a few quick announcements if you weren't in steel design. Class will be canceled on Wednesday. I will not be here. So I'm not going to be here. So you're more than welcome to show up if you want, but I won't be here. Okay. Last chance that I have to mention the technical conference. If you're interested in going, please, or interested in volunteering, contact the chapter president, Logan Stacks, as soon as you can. Also, if you're going to be there for a while and you'd like a name tag and things like that, you do need to register. If you're just going to peek your head in for a session and that's it, I don't know that you need to worry about it. But if you're going to be there for a while, then make sure you have your name tag. I didn't have this on the announcement slide, but homework is due today. So if you haven't already turned that in, go ahead and do so. I've got a pile started right here. You all can sort of walk them up here at your leisure. So make sure you're turning that in. I do have a homework for you also today, but it's not due for a while. It's not due till February 1st, so you've got plenty of time to work on it. In fact, while I'm thinking about it, I'm going to go ahead and pass that out. So this is referencing just some problems in the textbook. It's pretty straightforward. It's got 5 problems, and it may look like it's a long assignment. I don't really think it will be. I think especially for the first, initial problems, I'll be honest, there's going to be a fair amount of plug and chug. This should be uploaded onto Blackboard as well. So actually, let me just go and do this. There you go. There you go. All right. So this homework will be due on February 1st. Now, this homework does cover, hold on, everybody want to pay attention. This homework does cover some stuff that we're still talking about. For instance, we haven't gotten to nominal capacity or transformed sections yet, so I do want to try and get through as much as we can. But we should have plenty of time to cover these topics between now and February 1st. So we are still making some pretty good progress. Everybody good so far? Any questions? Okay. So today what I want to do is discuss transformed section analysis, and then hopefully we can delve a little bit into the ultimate capacity concept, or nominal capacity. In other words, this is the maximum amount of moment that a beam can see at all. Once we breach MN, that's it. The beam's done. So hopefully we'll get into that today. I did get the sign-in sheet started, didn't I? Yes. Okay. All right. I'm getting better at it. Okay. So real quick, so we've been talking about the concept of beam behavior. In other words, as we start to increase load, how does the beam respond? Now, we broached this concept of a cracking moment, the idea that under very low levels of loading, the could have gotten up. There's another. I'm just doing this all day. All right. All right. Let's get back to this. So we started off talking about low levels of loading, and we broached the concept of a cracking moment. The idea that under low levels of load, the beam responds like any other. But because concrete is a material that behaves weakly in tension, there's a point when the concrete just gives up and the steel takes over, and that's the cracking moment. Now, I think maybe there was a little bit of confusion about, well, if the concrete cracks, how does it grip onto the rebar? Well, hopefully I've got a little video here that might help explain what's going on. So I've got here a reinforced concrete beam test. Now, you'll notice the video states that this is a bending failure on the pile right there. On the video, the title lists the bending failure of an under-reinforced beam. That might not make a lot of sense right now, but it will later, because there are differences in the ratio of reinforcement that can go in concrete beams. And there's a very big difference between the failure of what we'll call an under-reinforced beam and a beam that's called an over-reinforced beam. And we'll get into that later when we start broaching topics of design. But I want to be clear what happens during the bending process. Now, I've got this beam and I'm applying load, and you can see the dials are cranking up, and you can see the loading is applied. Now let's be clear. Oh, let me pause it right there. Let's be clear. At this point, we've already broached the cracking moment because it might be a little hard to see, but you can see the cracks are forming, right here and here. We've already hit the cracking moment because it's cracked. That doesn't mean that the beam can stop taking load. That just means that the steel starts to take over. I mean, let's be clear. Our bending cracking is occurring right here. There's still concrete over here that's gripping onto the rebar and it's doing just fine. Okay? So the steel can still take over because the rest of the beam is still gripping onto that rebar, which that will bring up another topic we'll talk about later, which is the concept of development length. It's the idea of how far does a particular piece of rebar need to be embedded into concrete in order to develop its full capacity. And that's a whole can of worms that we'll talk about later. But does this kind of make sense? I mean, keep in mind, the beam has undergone its cracking moment, but you can see it's still accepting load. Okay? Sound good? Now you can see it's starting to give up and it's kind of softening. You can see it reached its nominal capacity. This is them zooming in on it a little bit, and you can see cracks are forming, and it's still accepting load. You can see there it goes, and then when you start to reach the compressive crushing stresses right here, that's when the beam basically kind of gives up. When the concrete in compression gives up, it's done. Okay. So far, so good? Any questions? All right. Now, just because I like showing these videos, this is an over-reinforced beam, and you'll notice the behavior is quite different. So the difference is this is a beam where it's concrete beam as usual, only instead we threw more rebar into it. And when you throw more rebar, you'd think that'd be safer. Not necessarily, because we have to obey this thing called equilibrium. And equilibrium states that the compression has to equal the tension. So if you throw a bunch of rebar into it, you're demanding more compression from the concrete all at once. So when it goes quick. So that's an over-reinforced failure. So sometimes throwing a whole bunch of rebar into it is not necessarily the right answer. So it's just something to think about for later. Let me say that. Okay, you're raising a good point. So in the world, all right. So I'll say this: in the world of beam behavior, we have three regions that we define. We have regions that are tension controlled, which means that it's largely governed by its behavior in tension. We have compression controlled regions, and then we have a transition region. When we're in beam design, though, we want our beams to be tension controlled. In other words, we want the steel to yield before the concrete crushes, because in that instance we have we have presence of large deformations, and we get a little bit of quote-unquote warning that the beam is going to fail. If it's governed by compression-controlled behavior, when it goes quick. So and that's something we don't want to happen. So, does that make sense? But I would, to succinctly respond to your question, what I would say is just right is under-reinforced. That's just right. Does that make sense? We'll get into this later. Yes, sir? Are you talking about like fiber reinforced mix or fiber reinforced bars? Yeah. I mean, and there are other grades of concrete. I do a fair amount of research with a material called ultra high performance concrete, and it's basically a particular type of mix where essentially steel fibers are thrown into the mix, and you can get some compressive stresses that are like 20,000 psi easy. The problem is it's expensive, so you can only use it in appropriate details. But yeah, I mean, they do that, and it's just going to change your FC prime, and it may change your behavior a little bit. But you start getting into when you start getting into that, you start getting into more advanced topics in concrete design. And right now, I'm just trying to focus on basic stuff. So I want you to be able to handle normal, regular old concrete before you can handle all the fancy stuff. So, sound good? Okay. So let's say that the beam has cracked. Let's say we have broached the cracking moment. So that means essentially the steel is starting to take over. Now, in our analysis, what we do to be conservative is we say that any concrete that's in tension, we just assume that concrete to be ineffective. So if we samurai sword or lightsaber through the cross-section, we end up getting something that looks about like this, I would say. Maybe I should draw this over here on the side. So if we samurai sword or lightsaber through the section, we would get something like this. So we have the neutral axis right here. We have the concrete above that's in compression. And in tension, all we have is the rebar. I mean, I'm not saying there's not concrete there. I'm just saying we're assuming it to be ineffective. It's not really doing us any good. So if you want, you can think, yeah, there's a beam down there, but we're just not considering it. Okay? Sound good? Now here's the problem with that. The problem is that I now have a cross-section that's got two materials in it. So if I samurai sword through the beam, I've got part of it made out of concrete and part of it made out of steel. The problem with that is if I start breaking out mechanics of materials or deformable bodies, if I start breaking out sigma equals my over I, the problem is that sigma equals my over I becomes invalid when you have a beam that's made of multiple materials. It doesn't work. Sigma equals my over I assumes that your beam is made out of wood or made out of aluminum or made out of copper, not out of concrete and steel. It doesn't work. So what we're going to do is this. We're going to, quote unquote, transform this lump of steel into an equivalent lump of concrete. So our cross-section is really going to look like this. We're going to have concrete above the neutral axis in compression, and for the tensile region, we'll sort of have this lump of concrete that's representing the steel. Once we have this, then we can start to use sigma equals my over I and all those equations that you learned in 216 to address some of these stress issues. So far, so good? Okay, all right. If that's the case, then I want to go into the following example, okay? Now, I want to calculate the bending stresses in this beam using the transformed area method. So we're going to assume that this beam is being subjected to a bending moment of 70 foot kips. We're using a concrete strength of 3,000 psi. I want to determine the stresses. Now, a couple things I'll point out. All right, I'm, again, being very choosy when I use my symbols. For instance, B, I'm saying, is the width of the beam. Okay, D. Now, this is a D. We're going to use D quite a bit throughout this semester, so this is something you'll want to pay attention to. Notice how D is the distance from the top of the beam down to the center of the rebar. Okay, it's not the height of the beam. Okay, it's the depth from the top to the rebar. By and large, when we do our design calcs later on, we're not going to really care that the beam is 20 inches tall. We're going to care more about the distance from the top of the beam to the rebar. That's going to matter more to us than the height. But we'll get into that later. So far, so good? Okay. Now, we do need the height, however, to determine the gross moment of inertia, because what I want to know is this. We're calculating the bending stresses using the transformed area method or transformed section method. It's the same thing. That assumes that the beam has already cracked. So I want to see what is the cracking moment of this beam, and have we already broached it. So let's just sort of play around with that and see what we get. So, okay. All right, so let's play around with this. Let's see what we got going on. Okay, so let's start off by determining the cracking moment. Now, by now, you should have enough experience, or enough experience with the examples that we've done to determine this. So let's do this. To determine the cracking moment, we're going to need some values. Somebody start spitting out some values, and let's see how we discuss them. So what's a value we're going to need to determine cracking moment? The modulus of rupture, F sub r. So how do we compute F sub r? There we go. So F sub r, 7.5, bless you, lambda. square root of FC prime. Okay, so let's start plugging in some values. Now we'll assume this is normal weight concrete, so what's lambda? 1. And what do we do for FC prime? Square root of what? There we go, 3,000 psi. We plug in psi, we get out psi. So what is that? What's that? No. No. When you see a square root of FC prime, that's a good question. When you see a square root of FC prime, put in psi and you get out psi. If you put in ksi, you could say you'll get out ksi, but I'm telling you the answer will be wrong. And you could test that. Well, we could test that here in a second. All right. First off, give me this. What do we have here? 410.8 psi. Okay. So do this. All right, 3,000 psi equals how many ksi? 3. So do 7.5 times the square root of 3 and tell me what you get. You don't get 0.4108, right? Okay, so yeah, always put in psi and get out psi. That's a good question, and unfortunately, it's very easy to test. So, sound good? All right, what else are we going to need to compute the cracking moment? Moment of inertia, or gross moment of inertia. So how do we compute the gross moment of inertia? The h cubed over 12. So what is that? Tell me what to do. What's b? And what's h? No. For now, we're looking at the whole beam as if it was one cohesive material, so we'll use 20. I'm saying later on, that's supposed to be 3. I'm saying later on, like in a few weeks, the h isn't really going to matter to us. Right now, for this calc, it does. So what is this? Say it again. 8,000. 8,000 what? There we go, inches to the 4th. We're also going to need y sub t. That's the distance from the centroid to the extreme tensile fiber. Remember, either the way tippy top, or in this case, because we're looking at tension, the way bottom of the section. So how far is it from the centroid to the way bottom? 10 inches, right? All right. Sound good? Okay. So if I've got all this, how do I compute the cracking moment? What do? Plug and chug. And what's the formula? There you go. So therefore, cracking moment equals FR times IG over YT. So what's that come out to be? It'll be a pretty big number, and that's fine. Say it again. 328,640. Now what are the units for that? It's a moment. Inch pounds. Now, anybody remember my little shortcut to get that into foot kips? Divide by 12,000. So what is that? 27.39. Foot kips. Somebody tell me something about that value in regards to this problem. Yeah, exactly. We're putting 70 foot kips on this beam. It can only handle 27.39 before it experiences its cracking moment. I'm not saying that's the maximum capacity. The beam can, withstand a whole heck of a lot more before it fails. I'm saying before it cracks, it'll crack at 27.39. We're putting 70 on it. So we've definitely broached the cracking moment. So we're definitely in stage 2 once the beam has experienced cracking. So I'll put what I'll say is this. I'll say M applied is greater than the cracking moment. So beam has cracked. I can do better than that. There we go. All right. Sound good? Okay. So, in order to handle this, we're going to need some values, a couple things. So we need to do a transform section analysis. We're going to need a few values. I'm going to walk you all through this. So the first thing we're going to need is a modular ratio. Now a modular ratio, the denotation for that is a little n. Okay? Now to calculate the modular ratio, we're going to need two things. We're going to need the modulus of elasticity of steel, so E sub s, and we're going to need the modulus of elasticity of concrete. Now first off, the modulus of elasticity of steel is a constant. Remember what that is? 29,000 what? KSI. Okay. So if you want, bless you, if you want, you could, if it's hard to remember what E sub s is, you could put E sub steel. That helps. And that's 29,000 KSI. Okay. Now, that's for steel. What about for concrete? Okay, for concrete, we're going to have to compute that. So you all are going to have to dig back through your notes. It's in there somewhere. And tell me, how do we compute the modulus of elasticity of concrete? It's in there. Make you all do some research, going back through your notes. It's like I'm trying to get you all to learn something. It's crazy. I know. Who do I think I am making y'all trying to get y'all to learn something?
3 times WC raised to the 1.5.
Times the squared. Okay. All right. So what slide number are you on?
Slide 56.
56. So if you're still looking, find slide 56. Okay, now, the equation that you read was the correct equation for any type of concrete out there. Okay? However, since we're dealing with normal weight concrete, we have sort of a shortcut. And what's the shortcut that we can use? There we go. 57,000. Does everybody see that? So 57,000 times the square root of FC prime. And for most cases, that's going to be good enough for government work. Okay. So 57,000 times the square root of FC prime. Okay. So tell me what to do. What do I plug in?
You plug in the FC prime.
And what is the FC prime? That's all right. There we go. This is my point. 3,000. 57,000 times the square root of 3,000. Now, what units is that going to give me? PSI. There we go. So plug that and tell me what you get.
3,122,000.
All right. So 3,122,000 what? 18. PSI. Okay. Now that's PSI. What's the problem with that? Needs to be KSI. So how do I do that? To take 1,000 off of it. So if I want, I could say 3122.02. That's good enough. Actually, you could probably just do 3122 and that'd be fine. All right. Sound good? To calculate the modular ratio, we're going to take E steel divided by E concrete. So 29,000 KSI over 3122.02 KSI. The decimals really aren't going to matter.
So are we transforming it into steel or into concrete?
We're transforming it into concrete, and you'll see how we're going to go about that. But All right, so to answer that question twofold, what I'll say is this. We are transforming the steel into an effective lump of concrete. But to calculate the modular ratio, the easiest way to remember is you always take the bigger number divided by the smaller number. So let's say that, I don't know, 2 decimal places, what does that come out to be? Say again? 9.29. All right, do I have a second on that? Okay, all right. Now, that's the computed value of modular ratio. By and large, when you're performing these type of computations, it's very conventional to just take this number and say, close enough for government work, let's just round that to the nearest integer. So for our purposes, we're going to take n to equal 9. We're just going to round to 9. So we'll say take n to equal 9. So far, so good? Okay. All right. I'm going to go ahead and move on to the next slide if you all are good. Okay. Okay. Hope you all remember how to solve quadratic equations. It's on the Casio. Oh, it's there. Hit mode, number 5, and then number 3. All right. Okay, transform section. So we've got an n value of 9, and we also are going to need the area of steel. Now tell me a little bit about the steel in this section. What reinforcement are we using? Three number 9s, right? So going back into your notes, I'm making you turn pages in more, lest you remember, what's the area of one number 9? No, that's, I know where you're thinking that you always take the value and divide it by 8, but that only works up until a number 8 bar. Number 9s are unique. 1 square inch. Now, what slide are you finding that on? 63. If you go to slide 63, you'll see the areas of conventional bars. Remember, I told y'all that's one you really need to put a bunch of stars on. I don't know what that was. The area of a single number 9 is 1 square inch. So 3 number 9s, that's 3 square inches. And I'll put 3 number 9s. I know where you're saying that it would just be 9/8, where the convention is to divide by 8. But that only works from a number 3 to a number 8. So if it's like a number 5, it'd be 5 over 8. But that's just the diameter. That's not the area. To calculate the area, you'd have to use pi over 4d squared. Sound good? Okay. Now, so here's what's going on our cross section. So we have a beam that looks something like this. Right? This is 12 inches. And we have 3 number 9s. And this is 17 inches. Is that right? Okay. Now, for a transformed section analysis, what we're going to do is this. Okay. Remember, we assume that all the concrete above the neutral axis is effective, but everything below isn't. So this is still 12 inches. But this distance right here, this one right here, we don't know what that is, okay? Because the point is to try and figure that out. So because we don't know what it is, I'm going to use the basic mathematics convention and call that x, okay? I don't know what that is. We're going to try and figure it out. All right. Now down here, we're going to have this sort of lump of concrete right here. And that lump of concrete is going to kind of replicate what's going on with this steel. So this steel has some area, some, 3 square inches? I propose that we have 3 square inches of steel to develop that same amount of stress with concrete, we're going to need a whole lot more concrete. Does that make sense? Concrete's a weaker material, so we're going to need more of it. So I propose that the size of this lump is going to be NAS, which is going to be 27 square inches. That make sense? Everybody okay with that? Now, let's get some dimensions taken care of. Okay? Now, the dimension from here to here, okay, this is still 17 inches. Okay, we're still putting that effective lump of concrete where it needs to go, to simulate the effect of the steel. Okay, what I need to know is this. Somebody tell me what is that dimension right there. Say it again. There you go. 17 minus x. Now, is everybody okay with that? Okay. Now, since we're dealing with bending and dealing with moments and things like that, I propose that to determine the unknown being x, all we need to do is sum moments. Now I'm going to sum moments about the neutral axis being that dashed line. So that's the neutral axis. So if I sum moments, about the neutral axis, what I'm doing is I'm saying basically the moment contribution from the compressive region must equal the moment contribution from the tensile region. And all I need to do is just treat this as if they're areas since we're dealing with the same material. So let me walk you through this. Let's deal with everything above the neutral axis. Okay? So what is the area of the region above the neutral axis? 12x. And I'm going to say all units are inches, because I'm going to sort of soft pedal the units as we go through this. So the area is 12x. Now let's talk about the moment arm. How far is the moment arm from the neutral axis to the centroid of that region? 12x times what? X over 2, right? Because the centroid of that region is going to be somewhere about right there, right? So 12x times x over 2, that's the moment contribution from everything above the neutral axis. That's got to equal everything below the neutral axis. So what's going on below the neutral axis? What's the area below? Say it again. 27. Yeah, that's what the NAS is. So 27 times, what's the moment arm? 17 minus x. So now this becomes a problem from what, Math 127 or what have you. So everything on the left side, we got 12x times x over 2, so that's what, 6x squared, equals everything on the right. So we distribute that out. So 27 times 17, that's 459, minus 27x, so that's 6x squared, plus 27x minus 459 equals 0. Told y'all we'd have a quadratic equation to solve. Remember, what is it? It's mode 5, 3, and then you can just enter in your constants. And we should get two answers. 6.78. So we'll keep it to 3. We'll say 6.781. Is that right? Okay. And x sub 2 is what? 281. Okay. Everybody getting that? Now, which answer doesn't make any sense? The negative, right? We're talking about a distance. So a distance measured down below the beam. That negative obviously doesn't make any sense. So And you'll either get one of two responses. You'll either get a negative answer, or you'll get some answer that's like 30 or something. That's greater than the depth of the whole beam. That doesn't really make any sense either. So, and that tends to happen on a lot of the calculations that we perform, that you'll get two roots, and one of them just by observation ain't going to make any sense. Okay. Sound good? Okay. If you've got this, then you can go ahead and determine your transform moment of inertia. And this is actually a pretty straightforward computation. Okay? So it's very similar to what we did before with that T-beam. We're going to draw a similar table. So we'll say shape and go to work. Although the nice thing about this calculation is, remember how we had like an A, and we had a Y, and we had AY, etc., and we had all of that? We did the A and the Y and all that because we needed to determine where the centroid is. We don't need to determine where the centroid is because we know where it is. The centroid is 6.781 inches from the top. So our transform section analysis is a lot easier. So we're going to start off by calculating the moment of inertia. That's going to be pretty simple. Okay. Now for this cross section, we got two shapes, right? We've got the concrete and we got the steel. So let's start off with the concrete. Okay. Now this region of concrete above the neutral axis is a rectangle. Okay. So help me out. How do you compute the moment of inertia of a rectangle? BH cubed over 12. So I propose that to compute that for this particular rectangle, it's going to be 12 times 6.781 cubed over 12, and that's going to equal what? Yes, that is correct. Say it again. 45.98. I got something a little different. 311.18. 0.8. Was it 0.83? I'm kidding. I'm kidding. All right. I'm going to work on just the concrete, and then we'll go back to the steel. So here's the moment of inertia of the concrete. Now we're going to need a couple things. We're going to need the area. How are we going to compute the area of that concrete region? Just 12 times 6.781, right? So 12 times 6.781, and that's what? 81.37. Okay. Now, that's the moment of inertia. We got the area. We also need the distance for I plus AD squared. Now, the distance is how far it is from the neutral axis to the center of that rectangle. So how do we find that out? How do we go from the neutral axis to the center of that rectangle? There we go, 6.781 over 2. Now what's that? 3.39. Sound good? So that's I plus AD squared. So tell me what you get for that first row. $12.36, you said? 1246.91, so 1246.9, something like that. We'll just keep it like that. Okay. Everybody okay with this? Now, that's the concrete. Now let's look at the steel. Okay. Now here's what might be a little strange. But what we're going to do is this. Now, how would you compute, let's just conduct this as a thought experiment. How would you compute the moment of inertia of the steel? Looks like a rectangle, right? So BH cubed over 12, right? But how tall is it? Say again, you're right when you say that, not very. What we're doing when we, when we assume that, I use the word lump of concrete. That word was actually chosen very carefully. I'm essentially just lumping all of that area at one particular point, okay? So what I'm basically assuming is that I have an area, 27 square inch area, but it really doesn't have a height. It's just a lumped value right there. So what I'm getting at is that the moment of inertia, the individual contribution, or the I sub O for that given value, I'm just going to take that to be 0, okay? Because it's just a lumped value right at that point. Basically. But you might be wondering, well, how does it contribute to the section? Well, it's not the I sub naught, it's the AD squared. What is the area of that steel going to be? 27. So it's going to be 3 times 9, which is 27. Now, how far is it from, bless you, from the neutral axis to the steel? Say it again. 10.219 or 10.22. And you found that by saying 17 minus 6.781. And so that came out to be, just for purposes of calculation, 10.22. Make sense? Now, tell me what I plus AD squared is. 2819.5? I'm easy to get along with. We'll just say it was the first one. Do I get a second on that? Okay. So sum those values up, and what do you get? Everybody get that? Everybody good? So here's what I propose. I propose that the moment of inertia of the transformed section is 4066.4 inches to the fourth. Okay? Now let's talk about that value. Does this value make sense? Think about it like this. What was the gross moment of inertia? 8,000. Okay? So let's think about what we're talking about here. We're talking about a beam that's already cracked, right? We're asking ourselves, how strong is this beam after it's cracked? Now I propose that the moment of inertia is a measure of how stiff a section is under bending. Okay, that's what it is. That's why we use sigma equals my over I. Before the cracking moment, we had a moment of inertia of 8,000. After cracking, we have a moment of inertia of 4,066.4. Does that make sense? I think it's cracked, so now the beam got weaker. It didn't completely fail because the steel took over, but it is flexurally less stiff. All right? Does that make sense? Everybody okay with that? Okay. All right.
What is TR subscript?
Transform. Just this part right here. Transform. Sometimes it's referred to as I sub CR, just the cracked moment of inertia after it's cracked. So either one's fine. All right. Sound good? Okay. Now, okay. The question, though, is we still need to compute our bending stresses. This is example 4. Okay. So we still need to compute our bending stresses. So let's look at this. So we have a moment of what, 70 foot kips? Now, just for the heck of it, I'm going to have all my stresses reported in PSI terms. So how do I get this to PSI? Or not PSI, but inch pounds. What was my little shortcut? multiply by 12,000. So if I multiply by 12,000, that's 840,000 inch-pounds, right? Sound good? Okay. Now, we have a moment of inertia of 4,066.4, right? Inches to the fourth. And we had an x value, and I'm just going to keep it simple. It was what, 6.78, right? So we've got, our beam that looks like this. We've got our lumped concrete. This is x, and this is 17 minus x. Make sense? Okay. Now, let's start off with the compression region. So the compression region, we need sigma equals my over I. Remember, the y is the distance from the neutral axis to the way, way tippy top of the beam. So how far is it for compression from the neutral axis to the way top? The x, yeah, 6.78. So the compressive stress, or if we want to use the notation for the concrete spec, F, is mx over I, which is that times 6.78 inches to the fourth. So what do we get here? And we'll just do to the nearest PSI. $14.01. All right. Sound good? Okay. Now, for tension, we do the same thing, okay? We say my over I. Now, what's our y going to be for the tensile region? 17 minus x. But here's the thing. If I were to just compute this directly, I would be reporting the stresses still assuming that it's a lump of concrete. But it's not. It's a lump of steel, okay? So I'm going to take those stresses and I'm going to adjust them by n, okay? Because in actuality, the actual area is much smaller. So if you think stress equals P over A, the actual area is much smaller, so the stresses are going to go up. So that's why we multiply by 9. So 840 17 minus 6.78 times 9 over 4066.4 inches to the fourth. And what does that come out to be? Say it again. 1900? Did you multiply by 9? I got something like 19,000. And my answer is like 18,966. You got, is it even? Okay, I mean, plus or minus a few PSI. 19,000 though, even PSI? Did you missed a 0. And that's seconded, right? Okay, all right. Now we're not done because I just want to at least introduce the next few topics. But before I move on, are there any questions?
Do you always multiply that expression by n because it's a stronger material?
Yes, because Well, let me say this. We do in this case because we took the steel and converted it into a lump of concrete. If we had worked backwards, this wouldn't be adjusted by M, but this one would have been divided. You see what I mean? Everybody else okay with that? Okay, now, a couple things. Look at these values. These stresses are much larger than the stresses that we saw before, right? But they should still be well within what the materials can handle, right? What was the compressive strength of the concrete we used in this example? 3,000 psi, and that's 1,401. So we're getting there, but we're still not there. And steel, I mean, heck, steel usually goes for rebar for 60,000 psi. So we're still, we still got a ways to go. This isn't ultimate capacity, okay? Ultimate capacity does take a little bit of discussion. Now, the complicated part regarding ultimate capacity is that your bending stress profile is not linear. It's nonlinear because your concrete is a nonlinear material. To explain that on Friday, I'm going to break out the C word, a little bit of calculus. I know.
Calculus is the real secret.
But ultimately, let me back up. Ultimately, the long and short of it is this. The calculus that we're going to use is merely for explanation purposes. The point is to try and come up with a way of assessing ultimate capacity without using calculus. So I'm going to show it to you once so we never have to look at it again. Is that okay? Well, you'll have to deal with it. All right. Sign-in sheet, if you haven't signed it, please do so. If you haven't got your homework up here, you need to do that. That's all I've got for you today. I will see you on Friday, okay? We'll see you.